All right, for anyone who's interested, we're going to be doing a Science on a Sphere presentation called One Ocean. So if you haven't got a chance to see this big, amazing 6-foot animated ball, this is your chance to check it out, and we'll get up and move around a little bit too. So get your daily exercise regimen in too. All right, we ready to go? All right, hello everyone. My name is Leon Geschwin. I work for NOAA, the National Oceanic Atmospheric Administration, in the Office for Coastal Management. And I want to welcome everyone here to Science on a Sphere. So I want to start with this image. This presentation is called One Ocean. And this image you see here, you'll notice a big landmass and one big ocean. Anybody want to guess what this image is about? Any guesses what we're looking at? Sea level rise? Okay, what else we got? Good guess. Yeah? Pangea. Good, we're really close there. Actually, this is, Pangea was back 250 million years ago. This is Kenosha, which is 600 million years ago. So I wanted to start with that to give you some sort of historical and geological perspective that back then we really were one ocean. And we'll talk today about how our oceans really are still interconnected. I just added this in recently just because people go, well, how did things change over time? And this is one of my favorite animations showing the paleogeographic evolution of the Earth. As continents move throughout time, you can see the years there, and as it's advancing, and the Earth really hasn't been stationary, right? Plates are constantly in motion, and we're going at the 400 million years right now. And just sit back and kind of watch and get an idea of where, see if you can recognize continents at a certain point in time. So here we're coming up on the age of the dinosaurs, beginning about 250 million years ago. Here is Pangea, right there. So we're beginning to see some continents, South America, there's Africa, there's North America, and the beginning of the Atlantic Ocean forming. So this is taking that image previously and just moving it forward in time, getting a lot of this data from paleo-magnetic data. As the magnetic fields flop back and forth, we're able to piece back how the plates move throughout time. And then coming all the way to today, if we zoom over to Hawaii, you can see the Hawaiian Island chain, the Emperor Seamounts, and then the Hawaiian Island chain right there. Yeah. Well, that's our highlight. Thank you very much. So, a little bit about NOAA. So this is our big advertisement here in terms of what... Anybody know what NOAA does, what NOAA studies? Let's hear it. Any clue? Ocean. The ocean, all right. What else? The atmosphere, weather, tsunamis, right? We hear all those things. NOAA, our tagline at least, says we study everything from the surface of the sun all the way to the depths of the ocean. So here we have the surface of the sun, and then we're going to go ahead and drain away all the oceans. And so it's a pretty big responsibility here. Today we're going to focus in on the oceans and, as I said earlier, how these oceans are sort of interconnected. First, a little bit about the technology. People look at this thing, and then they spend the entire presentation thinking, how does that thing work? And they don't listen to anything you're saying, all right? So we'll start with how this thing works. Anybody seen, who's seen Science on a Sphere before? Hands up. All right, a few of you. Where did you guys see it? Here, okay. Besides here. Yeah. At the IRC, at the NOAA Regional Center. So there are a number of Science on a Spheres around the world, and this is a little animation. All those pinpoints are where you can find a Science on a Sphere. So there are over 130 of them located around the world at different science centers, museums, aquaria, government institutions like NOAA and NASA. Here in Hawaii, we actually have 3 spheres. We have one at the Bishop Museum, so if you want to get more of your fill. So in the Bishop Museum, there's one that was recently installed at the Inouye Regional Center on Ford Island. And there's also one on the Big Island at the Imiloa Astronomy Center. And the way the sphere works, if you look around the room, a lot of people in a completely dark environment, it looks like a hologram that's up there. Here we see a little bit more of the back end, but there's 3 steel cables up here. This is a 50-pound 6-foot ball suspended from the ceiling, and there are 4 video projectors, 1, 2, 3, and 4, all connected to a central computer that does some sophisticated software behind the scenes to blend, wrap, and have a nice, seamless image of the Earth. So pretty cool technology, and a lot of cool places that you can see it. So let's start with our Earth, the blue marble. Now, imagine yourself as an astronaut floating above space, looking down at the Earth. Right? This is maybe a perspective that you get. What do you notice about our planet? Lots of water, right? Lots of water. Over 70%, 71% of our planet is covered in ocean. So to get a little better view of the ocean, let's go ahead and strip away the clouds. And you can really get a good idea that even places that aren't covered in ocean, you see up in the poles, the ice, all different forms of water there. So how do we collect these types of data? Like, how does NOAA get more information about the oceans? Satellites. All right, let's take a look at some satellites. Good. So we'll start, jump around here. This is an animation showing you some of the different satellites around the Earth. You'll notice some look like they're broken. They're not broken. These are geostationary satellites. As the Earth rotates, they keep the same rotation as the Earth. They're about 20,000 miles, 30 kilometers above the Earth. And to get you some perspective, let's imagine now that this were the actual size of the Earth, all right? And we're going to scale it up. Can anyone guess how far you think these geostationary satellites might be? All right, so it's a guessing game. Where do you guys think these satellites are located? 20,000 miles. So scale this down to the Earth. Where do you think these satellites are located? I'll give you an idea. It's like they take these scan lines. So they don't take a single image, but they take scan lines back and forth. And the one situated over the U.S. goes east and goes west that provide this hemispheric view of the Earth. How far? Do you think they're this far? Getting hot, cold? What do you think? Here, right, this is like Marco Polo or further. Yeah, actually you're good. You're right on it. So I'm not going to jump into the crowd here, but it's about 16 feet. So imagine yourself 16 feet away. That's so maybe you guys way in the back there are geostationary satellites there. Right? So we have these geostationary satellites, but they're also coupled, and we get observations from polar orbiting satellites that orbit from pole to pole, as the name indicates. They take about 90 minutes, an hour and a half or so to orbit the Earth. And within a day, you're able to get a complete picture of the planet. So here's an image showing one of these satellites, Aqua, and it's taking these swaths or strips of data over time. So you just rotate this around, and you can see how it builds up a nice complete picture of our planet. These are flying a lot lower, right? As they orbit our planet, they're about anywhere between 400 to 500 miles, 800 kilometers above the Earth. Where do you think that would be in relation to the Earth? Yeah. Further? Closer? What do you guys think? Oh, here we got someone calculating it in their head. So what's the answer? 16 feet. It's actually right about here. Right, it's about 4 inches or so. Right, so that gives you some perspective in terms of these satellites, right? Geostationary runs way out 16 feet, and 4 inches above the Earth, we have these polar orbiting satellites. So besides satellites, right? Yeah, go ahead.
The closer in, the faster they go, and the further out, the slower they go.
Right. Oh, that's a good question. So besides satellites, we need to fill in the gaps, right? Satellites only get information from a very thin layer around the oceans, but what about stuff that's much deeper? How do we get information about those? What types of instruments might we use? Or buoys, right? Let's check out some buoys. All right, jumping around here. So these are just one set of buoys called the Argo Buoy Network. There's over 3,000 of these situated around the world, and they're located about 200 miles, 300 kilometers apart from one another. And the way these things work is they stay at depths of about 6,500 feet, about a mile or a kilometer and a half, and they record temperature, velocity, salinity, these types of water quality parameters. And on the 10th day, these things rise up to the surface, and they send that information up to a satellite, and they go back down, and they repeat the process. So you're able to get this amazing, not only information about the surface of our planet, but also depth going down to a kilometer and a half. You'll notice these things are moving. What's going on there? Is this, why are these buoys moving? Everybody know? Currents, right? They're driven by currents, right? So let's take a look at some of our currents. So here is an image of our sea surface currents. The colors indicate how fast those currents are moving. So dark blue are slow-moving currents, and as you get into the greens and yellows, they become a lot faster. So where are most of the quick currents here? Yeah, along the equator, right? They're wind-driven currents that you see here. Now we can look at these currents, and we can combine. The neat thing about the sphere is we can combine different data sets with one another. So we can take currents, we can overlay them on sea surface temperatures, and really see, this is also one of my favorite sphere images, looking at how warm water is transported from the equator. We can look up here, classic example, up the equator, up the eastern seaboard, and then transported through the Gulf Stream all over here to Europe. So Europe gets these nice climates because of this transport of heat that's occurring there. Any questions so far? I'd love to entertain questions throughout. Just yell out a question. More interactive, the better. Let's take a look at what's going on in Hawaii too. This one I can just sort of watch for a long time and look at these different eddies and currents as they flow throughout the Earth's surface. Yeah, so this is Yeah, so the question is, well, she noticed the data was at 2007, 2008, so this is sort of a nice visual piece that's put together. But we can also look at currents as they occur right now. So we can look at, so this is one showing sea surface temperatures, and this is a year's worth going all the way up to today. So we're able to get stuff that's historical and sort of produce nice animations, but we can also get stuff that's more real time. So this is the El Nino that occurred last year. How many of you have heard of El Nino before? Right? You've probably heard in a lot of presentations, but that's that warm water tongue that exists off of the west coast of South America. So I'll rewind it just so folks can see it again. This is one of the major El Ninos on record. And what happens during an El Nino is normally you have trade winds blowing from the east to the west that blows off that warm water. You have cold water upwelling, but during an El Nino those winds slacken. You get this warm water pool off the coast of South America. And it has huge implications in climate around the world. But yeah, we can show real-time stuff as well. Any other questions? Yeah. So the question is about, so I'll address that a little bit later in terms of organizations and how they use it. So maybe we can talk at the end about how people use the sphere and where it gets out to. There are over 130 sites, but there are a lot of different content creators from NASA, NOAA, universities, museums. We can definitely talk about that. So I showed you surface currents, but there's also a bigger story about currents that are happening at depth. And this is a model showing you our thermohaline. So this is thermal from heat and haline meaning salt, so our ocean circulation model that transports water at depth. So everything you see in red are warm surface, warm currents on the surface, and then things that are depth are ones that are traveling much deeper, that are saltier and denser. Now to get this a little bit perspective, to really show that we are indeed one ocean, there's a model here that takes, imagine a single particle. So let me rewind it just so we can get the full effect here. So we're going to start in year 0. Imagine a single particle of water here, and we're going to follow that through the global circulation, through the thermohaline circulation, and see what happens. So the colors represent the depth. So you can see as it's on the surface, it's being mainly driven by different wind patterns. Let's go around South America. And there's the Gulf Stream taking it up and across Europe. So this is just a model showing you how, what it would be like for a single water particle to kind of move around the globe. So it goes around some of these gyres a couple of times. Now we're up near Greenland here, so it's gotten deep and it's sinking. Yeah, go ahead. Right, so the garbage patch that you're talking are mainly driven by surface currents. Things that are much deeper here, this is much bigger circulation patterns. But this is deep, and if you look at the time scale, we're looking at 280, 300 years here, so a lot longer in time scale. So let me skip, I've been given the hook pretty soon, but I want to show you a couple of things in terms of how ocean temperatures impact different things like wildlife, for example. So this is a map showing you loggerhead sea turtles, and in the background are ocean temperatures. So red, orange, warm water, and blue, cold water. What do you notice about where those turtles are chilling out? Yeah, they kind of like this sort of narrow range of temperatures. So you can see how sea surface temperatures and the prospect of climate change and those sorts of impacts, how that might impact different types of critters like sea turtles. And finally, we have 5 minutes left. We talked a little bit about El Nino, and I just want to kind of point out, this is, I think, one of the biggest ones on record. You can see it pretty clearly outlined here, that red tongue of water off the coast of Peru there. Finally, how much time do I have? A couple of minutes? Yeah? Till 12? Yeah, all right, I got some time. Sweet. So let's look at some other impacts of, if we look at these, this is a ocean temperature model again. You saw one earlier, but this one really shows you the seasonal variation in temperatures over time. So northern hemisphere summer, things get warmer up there, and then it shifts southerly. And this is a really neat one, just showing you how seasons impact the world's oceans here. Another thing that impacts or is impacted by seasonal variations is sea ice. So we'll take a look at sea ice. You'll notice we're just looking at the minimum sea ice here over the Arctic, which happens in the September time period. And we're taking it from 1980s and bringing it all the way up to today. Anybody notice any patterns in terms of the overall sea ice? It has some variation, but overall, what's happening to it? It's shrinking, right? It's shrinking over time. In fact, I just read about recently, there was this big luxury cruise ship. Did you guys hear about that? The first luxury cruise ship that's sailing up the Arctic. So it's going up through the Northwest Passage, all the way around, and then popping its way up around the Hudson, and then to New York they're ending. And I think recently they still haven't seen, even up the Northwest Passage, they haven't seen any indication of ice yet. So it really shows you, I mean, these concrete examples of, that number one, we're able to have these cruises up in the Arctic. I mean, two, that we're not even seeing ice in a lot of those areas. It really hits home. So those are, I talked a little about ice. I told El Nino, which is more of the indirect impacts of increasing temperatures. But some of the more direct impacts, I just want to jump to this because it's, again, one of my favorite animations, and that can really show globally, are tsunamis. So this is the tsunami that occurred in Japan in 2011, and the colored dots indicate the coastal run-ups in those areas. So as the tsunami propagates from Japan, you can see the time scale on there. We're 4 hours in. Now we're hitting the Hawaiian Islands at about 6 hours or so. And all the areas that are impacted from that tsunami. So in terms of colors, if you see it in red, those are pretty much indicative of a tsunami warning. Evacuate the shoreline. Orange, stay away from the coast. And green, you're okay. So you can see sort of the impacts. The tsunami in the open ocean is traveling as fast as a plane, about 400 to 500 miles an hour. So it's really screaming across the ocean, in the open ocean, and then it sort of scrunches up like an accordion as it gets to shore. You have these huge waves come alongside. You mentioned earlier about marine debris. Let me show you a quick model on that, just to get on some of the more fun stuff. So this is a model showing you we've dropped a bunch of buoys, dropped a bunch of particles equally throughout the world and let the model run. So this model data is showing you where these particles tend to aggregate. And it gives you a proxy for where a lot of these marine debris aggregate. So what do you notice? Anyone notice any patterns here? Right, so they're away from the equator, right? And they generally form in these gyres, right? So there's sort of the garbage patch there. If I can overlay some continent, gives you a better perspective into country borders. You can see how these particles move throughout time and really indicate the major gyres and where marine debris tends to show up. Another impact of, we talked about warmer oceans previously, apologize jumping around a bit, but one of the other major impacts is looking at coral bleaching, right? As we have warmer temperatures, corals get exposed to increasing levels of temperature, and this is looking at actual data that goes all the way up to today, showing you what areas are in watch, warning, and really alert levels, which means massive amounts of bleaching going on. So this is going all the way up to today, and you can see just here in the Hawaiian Islands, right, we're at sort of a warning level, which is indicative of bleaching, and if it continues at that rate, we'll have some big bleaching events here.
Doesn't appear to be many that have no stress.
Yeah, so I forgot to point out, everything that you see in purple, those are where the coral reefs are located. So there is, yeah, you're correct, especially here in the northern hemisphere. At this point, there are a lot of places that are being impacted a lot. Yeah, summer, but also we're coming off of an El Nino exacerbates a lot of those warmer ocean temperatures. So El Nino compounded with the impacts of climate change don't